What's coming off around here?
If you guys playing railroad anymore today, there's a landslide, a new cut.
It's been, I'd say 2 months. I guess it is. It's 2 months since my last post of a video. So I thought I'd catch up on sharing things that I'm doing. And what you see here, this is a project that is going to be in an upcoming video. I haven't started it quite yet, but I unpacked it. This is it's the Scenic Details Inslee Model K, the backhoe. And I'm going to use this, I think I may have mentioned it earlier, I'm going to use this with a clam bucket, which I also have a kit that I bought for the clam bucket. And it will be used in the yard for cleaning out the ash pit and loading coal for the steam operation. The service area is going to be for a short line type operation, so it's not going to need, you know, a big water tower and all those things. It's just going to be a simple equipment that would make sense for an operation of that size. So anyway, the part that I wanted to present, not this yet, but actually tell you more about what I've been doing. It's been 2 months and I've been active. I've been doing a lot of things, and not all my hobbies have to do with model railroading. And so I got vectored off on one of my other hobbies, and I'm willing to share that, but it's kind of boring software stuff. But in a nutshell, what I had done was I've been trying to polish up my chess game just for the fun of it. And so I built a code that would allow me to take PGN files, which, you know, for those of you who aren't unfamiliar with what that is it's a save file format for chess games that's pretty standard. And I wrote a code that would allow me to translate the actually translate from a different format into PGN, because I had written, I don't know, I guess it was about, I think maybe 10 years ago, I wrote a Java application, not to be confused with the Java script language that you find on the internet. This Java, straight up Java compiler. And I wrote it that it would allow me to replay PGN files so that I could study my mistakes and try to catch those types of mistakes, not repeating them in future games. And so having that PGN reader, when I play this, there's another game that's available on the internet that doesn't save in PGN. It actually uses a game format, which actually was kind of mysterious to me when I started looking at the binary, but I translated that into PGN file, and it took me a couple of weeks to do that. Actually 4 or 5 weeks, to be honest. It was hard to figure out because it wasn't documented. I've never seen .game format before, so I had to kind of hack through it and turn it into an actual translation into PGN. So that's what I've been doing, some of what I've been doing anyway. And so moving on, I also have been making progress with the USB shield that I've been boring everybody with I actually got it to work, and I did a lot of development with a driver for the USB interface board that NCE offered me. I have that board, and, you know, as you see, I've been trying to make it communicate. So I'll share some of that in this video, and not try to go too deep in detail, because I'm not sure how much anybody really wants to know about the USB host shield library or the host shield itself. I pretty well covered the host shield, and I think that I made it clear that I was pretty unhappy with it. But I did find a way, after a lot of experimentation, to get it to work pretty reliably, and well enough that I could do the driver development. What you see here is the manner in which I was able to get this host shield to function very reliably. one of the major causes for my frustration was the fact that I was never able to predict when I was going to plug in a device and have it simply not be recognized. So in this kind of configuration, I've been successful. And what's happening is that I've used the voltage divider that actually I had discussed previously and reduced the 5-volt output from the select. Now this select part of the SPI interface is active low. So it's typically high most of the time. So that's that 5-volt signal DC being applied to the host shield, and as was pointed out, causing a problem with the 3.3 volts on the controller chip that does the actual heavy lifting on the USB interface. So having cut that voltage down with the divider to 3.3 volts, this has become actually quite predictable in terms of its connections, detecting connections. I mean, occasionally when I was working on the driver for the NCE USB interface board, that, occasionally I would plug it in and it just wouldn't see it, it wouldn't detect it, but just by unplugging and replugging it back in again, it would then see that there was something attached and I could communicate with it. So this was basically a must-do in order to get this board to work correctly. And I don't know that, I still have very low regard for this particular product, but there may be other products. Some people might find something else that's much more functional, but this one, I just couldn't see ever buying another one. So that's my opinion. So let me move on. I'll show you what I did also, some additional work on the Bluetooth. I've created a succession of Arduino applications to investigate how the JMRI Decoder Pro would communicate on a Bluetooth serial channel. I had examined and explained in painful detail how to hook up and connect the Bluetooth module in episode 17, part 2 of the JMRI via Bluetooth serial video. And in that video, I used a program on the laptop called Bluetooth Serial Terminal to establish a connection with the HC05 module. I also mentioned in that video that when Windows connects with the HC05, it always creates 2 COM ports. And at the time, I just didn't know why, but since that video was published, I've connected the JMRI application to the Bluetooth COM port, and I found out why there are 2 COM ports and more. First, I discovered that Windows does not rediscover a Bluetooth connection with the HC05 in the way that it does for instance, a Bluetooth headset. Like, for instance, this guy here. When I turn that one on, Windows auto connects and sets it up. But for the HC05 module, Windows doesn't know what kind of module it is. And that feeds back to the explanation previous that you have to change the discovery from normal to advanced in order to detect the HC05. So I suspect that's a result of the fact that the HC05 doesn't identify what kind of device it is. So as I said, I discovered that with a Bluetooth connection with the HC05, it, in a way it does with that Bluetooth, like with the headset, it doesn't reconnect. But every time the laptop is turned on, it's necessary to repeat a series of these steps. First, you have to go to the system screen, then you have to select the Bluetooth and devices category, then you have to click on devices, the devices selection. Next, you have to, in the dialog displayed, the HC05 device will be listed provided it's powered up. You know, you have to have it powered up before it can be seen, of course. But if it's already listed, then that device entry in the list has to be removed and then added again. Now, ask me why, I don't know. It's not there. And if you were to look at that point for the COM ports that it sets up, they won't be there. So you don't have a connection at all. So the trick is to simply delete or remove that one that's showing, and then go through the reconnection process that I described previously. I think it's a result, like I said, of the use of the advanced discovery. God knows what that means. The other thing is the matter of the two COM ports created. Once Windows has the Bluetooth connection with the HC05, it's necessary to choose the right one, and you have to choose wisely. I discovered that each time JMRI starts, and there is a configuration it finds for its communication with the DCC controller, the JMRI immediately tries to communicate with that controller. And if the connection isn't responding, the JMRI simply locks up, and it seems to be just waiting for a response, but it never gets it. And so the only way to shut down JMRI is by using the task manager and force the end task. And the real down part of that is that it will repeat that lockup every time it's restarted, as long as it doesn't actually communicate with the device. So that can be a royal pain. Now, what I had found is that the fix required locating the configuration file and either deleting it or using a text editor to change the COM port assigned. Now, that configuration file is named profile.xml, and any text editor can edit this simple ASCII character file. Don't let the XML, the XML doesn't really mean anything special. It's just a particular format for a text file. So now, regarding the two COM ports, it's necessary to do the following to discover which one of your newly added COM ports is the right one to use. You have to open the Windows, go to Settings, then to Bluetooth and Devices, select Devices. Then you have to choose More Bluetooth Settings. It will show the two COM ports, and under Direction that you see there, it's going to say either, let me see, what was that? It said incoming and outgoing. Those are the two kind of COM ports you have. So you want to choose, once you choose this tab and you see the COM ports and you see what one's outgoing and one's incoming, it refers to whether Windows receives a connection as an incoming connection or it requests a connection as outgoing. So for JMRI to work correctly, you have to choose the COM port that is the outgoing COM port. So you have to do this every time you restart your computer. And this is quite simply, it's an inconvenience. Each time the laptop is turned on, I would like it to automatically connect, and it will not. So that's just the nature of this HC05 module. Well, there's more I'd like to share regarding the Arduino app I created to explore the Bluetooth serial COM port function with JMRI. The software that I'm showing here is a fourth or fifth iteration. An initial version I designed was simply to turn on an LED if any serial input was received from the Bluetooth module. As you can see here, there's a couple LEDs on the board, and I think it was the green one that I was turning on. So that trial then verified that the wiring to the Bluetooth module was correct, and that I also managed to sort out what Windows did with the Bluetooth signal it detected as the two COM ports. Then I spent several more trial sessions with JMRI learning how to configure the JMRI for a COM port. Then also why JMRI locked up each time, and then finally what the data meant that my Arduino app was displaying from the JMRI. So the Arduino code initially received a single byte from the JMRI of AA hex. Fortunately, the NCE USB interface ships with documentation. This, what I'm showing, is what I'm referring to. Then on this page, page 5, shown here, the AA is described as a request for the software revision number, and that it requires a 3-byte response. I started out with a 3-byte response by noting that when the power cab initially turns on, it reports its version is 1.65. The 165 bytes as a response didn't work with JMRI. According to this page on page 3 sheet of the USB interface document, the system software version 1.65 reports a different version to the PC. Of course it would. And that, in this case, would be 7.3 point something. And looking down the list here, you see that the power cab with a version of 1.65 reports 7.33. And those 3 bytes, 733, as a response to the Arduino, the AA hex that it received, resulted in a second byte from JMRI that was 21 hex. That 21 hex is the loco control command. Moving on to the USB Arduino driver, I've described how my preliminary effort was able to show the host shield library's running states from the initial disconnected state to the connected state. I also shared in that video that I was able to read the configuration data of the attached device. Well, in that case, it was my PlayStation controller. But for the driver code to function for my Bluetooth communications COM port, I needed to be able to transmit and receive data through the NCE USB interface board, which is this guy right here. So the data flow has to be from the power cab through this RS485 cable, through the USB via the NCE USB interface to the Arduino host shield. So the first step to that process was identifying how the end-to-end data transfer is handled by the system. From the experiments with the Bluetooth COM port, it was clear to me that the JMRI initiates the data exchanges with the NCE power cab. Now that would be the JMRI coming in on the Bluetooth. That's not shown here, but that of course would be plugged into this module. And it would be using on the PC the Bluetooth COM port. It was shown in the earlier video that the NCE cab bus uses the RS485 communication network to communicate with the interface board right here. So the NCE board's microcontroller is managing both sides of the data exchanges. The manner of serial connection to the NCE board's USB, right there, interface using the host shield library remain to be created. I don't even at this point have that completed, but I'll continue at least to explain what I've got. So reading the NCE interface configuration data out of this guy right here was done using the Arduino code demonstrated in the previous video. That was required for I needed to have that configuration data, and I needed this information that I'm going to show you here from that configuration data. The vendor ID is 1A86 hex. The product ID is 7523 hex. The USB version is 1.10. The number of endpoints available is 3. The interface class is FF hex. This code is the vendor-specific code, the FF hex code. In the USB specification, there are 15 class codes, such as audio, printer, mass storage, hub, etc. That FF code provides no useful information. It's vendor-specific. Now, the three endpoints are defined as an input with address 2 that supports bulk transfers, an output endpoint addressed also at 2 that also supports bulk transfers, and a third one, an input endpoint address 1 that supports interrupt transfers with the polling interval of 1. So what that means is that every 125 microseconds it can be polled using a high-speed device. And I'm pretty sure that these are high-speed devices. One little previous note made is that it was this JK connection information that defines whether it's a low-speed, high-speed, or ultra-high-speed type interface. And this was a high-speed interface. The direction of an endpoint is based on the host, so that an in transfers to the host and an out is a host to device transfer. My initial guess was that the NCE USB interface used the 2 bulk transfers for both in and out, but that didn't work for my driver code. The out transfer transmitted an AA command without an error, but the in received an ACK. In the previous video, which was episode 23, I discussed the host shield library's task method as it pertains to the startup function that detects when a device becomes attached. I also discussed the task's state-wise progression as the library code configures itself for that attached device. That's interesting to know, but however important detection and configuration is, it's equally important to understand how the library manages data transfers. And I discovered that when the library task method detects a connected device, it calls a library method named attempt config, which clearly, as the name says, it attempts to configure the attached device. This invites a side discussion about the host shield library's architecture. The library treats its USB function as a hub. Emulating a hub means that more than one USB device may be connected at a time. To accommodate multiple devices, the library implements an array named devconfig. I know, it's the configurations of the devices attached, I guess, is what they were thinking. Each entry in this array, which is indexed by a driver number, has the value of a pointer to an object of a driver class. Well, when I initially tried to create a USB app, the interface application, I did not create a driver class. I just started writing the code as an Arduino sketch. It puzzled me why that code would not compile with the library. It would not compile because the library's effort to register a driver requires a pointer value to an object. So creating an object of a driver class is required for using this library. But why, you might ask? Well, the object pointer in the devconfig array is used by the library to make a callback to that driver's init method. So, when it calls attempt config at the time that the device is detected, this callback takes place. Let me diagram this library architecture quickly. So let's say that you're creating a USB sketch for the USB host shield, and on that you have the sketch itself. And in the sketch, of course, it has the startup and the loop command. And in the startup command, it's necessary to create this object, but we'll talk first. Let's just discuss this thing. It has to have a class that defines a driver. So this class then has to become instantiated, to use the C++ terminology, to create an object. So in here then, in this sketch, you got to have the driver object, which is of this class type. So then this sketch also is linking itself via an include statement to the host shield library. So in this startup, when you initially create the host shield and you do a startup, the sketch has to do a registration of the driver with the library, so that the library takes this registration, which is a pointer, to, sorry about the sloppy, to the driver object. So the driver object now is installed in an array over here, which is that array I just mentioned, the dev config array. And because the library uses a hub model, and that hub model means that it's going to have in some array multiple entries of these pointers in this what's called the dev config. Sorry about that. It's hard to read, but it says dev config. That's the array. And that would allow then this host shield library to be able to manage multiple attached devices. We're not going to do that. Obviously, I didn't want to have multiple devices. I just want to have, my NCE USB interface USB device attached. So I just didn't pay much attention to this, but it was required by the host shield library in order to compile, and that is what I was getting at. Regarding the library's hub model and driver number, I'd like to share an important point. For a hub to have multiple attached devices, the hub must tell each attached device it discovers what its device number is. And then each device in turn must store its number and use that address to determine when the hub is communicating with it. For me, it was necessary to understand why my initial driver received an address not found in pool error message after I implemented the init function. And it was not implemented correctly. And so I took a little study to figure out that the fact is that the driver, as I said, the library, as it connects with an attached device, nulls out all of the endpoints except for 0. So all that information for the driver in this case, talking to device number 1, doesn't exist. And so it's necessary for the init function to create all that information. So as I just said, every attached device has an address number. The error number that I got just wasn't a matter of correcting my init method that my callback function in my driver class. In this method, the library's address pool it exists as an array of attached devices, and it's searched by the library for the next available null entry, and then that number that's available, the index, is assigned as the USB number for the newly attached device. It's a great deal more complicated than that, but the point is that I'm trying to make is having only one device, the USB is always 1. And the init method assigns the endpoint descriptor data to the address pool at device number 1. So now it's defined and that particular error goes away. The host shield library depends on a number of callback methods in the driver class, my driver class. And my class currently implements only 2 of these callbacks. One is the endpoint extract method and the other is init. And there are others that the library would like to call, and I just didn't need them. For instance, the on init, pull, parse, release, and get address. Let me quick diagram this callback technique the library is using. So to start with, just review this. This is the same diagram I just showed, and here we have the sketch, and here shows the driver class. And in a sketch, there needs to be an object created of type driver so that this object can call, obviously, the functions or methods, as you will, that exist here within the driver. And the object, as you know, for those of you who are familiar with C++, you can take the address of the object and we'll just say this. You can take the address of the object and it's pointing to wherever the compiler placed the object of this class in memory. So this object is now a pointer, and that pointer can be passed then to the host shield library by what is referred to here as register the driver. So in the host shield library then, it has a copy of this pointer, and in the library can then call a function that's defined here in the class by using the object and then this operator, which is dereferencing the pointer called object to call the function called init. Boing. So this then is a function call that's referred to as a callback, so that the host shield, having a reference to the object in the sketch, can now reference the init method that exists within the class driver. As I said earlier, my driver's not working. What I explained earlier is that the host shield library detects a device attachment, and then it reads that device's configuration data. This is the way that the device defines its data ports called endpoints. I'm again showing the NCE USB interface board's USB configuration data here. It defines 3 endpoints. See them right here. These are in addition to the endpoint 0, which every USB device must have in order for the host to get this control information. So it's showing actually 4 endpoints, and it's 0, 2, 2, and 1. And note that the 0 is, of course, the control endpoint. There's a 2 and 2, which are either one is the input and the other is the output. And then there's a 1, which is an interrupt input port. And what is a serious problem for my effort to communicate with the NCE interface board is the redundant endpoints at address 2. One is an input and one is an output, as I said, and USB has an absolute rule. This is the specification I'm talking about, that only endpoint 0 is bidirectional. That would mean to me that endpoint 2 must be either an input or an output. But yet here it's from the NCE interface that port 2 is both. That's which just doesn't seem right. It just doesn't seem, it's a little bit, it's troubling. But I also consider that perhaps the endpoint at 1, the interrupt input port, was being used for input instead of the port on 2. So I considered both. And what I discovered is that every example that is supplied with the library has unique port numbers, and worse, the library doesn't have the ability to interpret this duplication of endpoint numbers that I have coming from the NCE interface board. I'll show what I've created and what the results are. As just mentioned, I have two USB drivers. One uses the two bulk endpoints at 2, and one that uses a bulk out at 2 and interrupt in at 1. They're essentially the exact same code as I'm showing here. The driver object is declared as a global object here, and to conform to the library's requirement, I created an array of a single byte AA, shown here, also in the global scope. The AA it's a cab bus command that requests NCE PowerCab's firmware version. The library is included here, and an object of the library is created in the global scope here as USB. In the setup method, the library initialization is performed by this call to the library's init method. That completes the setup of the library and my driver. I'm showing next my loop code here. Every time the loop is executed, it calls the memory's task method here. The task repeatedly checks for an attached device and as the first step of a state machine. Detection depends on the Maxim 3421E USB controller chip's internal hardware, so correctly having the chip's 3.3 volt supply is essential. And as you recall, I went through all the process of using a voltage divider in order to make that happen. When the attachment is detected by the chip, the task method state machine proceeds to read the device configuration data via the USB endpoint 0. That's as I stated, the control endpoint. That data also contains the endpoint descriptors. The library performs next a configuration step that calls my driver's init method. The driver's init assigns a device number to the attached device. Now recall that the hub model requires that every USB device has to have a device number to distinguish it from others that may also be attached. Init next calls the library's get conf discr, it's GETCONFDESCR, or perhaps phonetically get configuration descriptor method. Recall that the NCE USB finds the 3 endpoints in addition to the endpoint 0. The execution of the library's get config descriptor calls my driver's endpoint extract for each one of these 3 endpoints. The extract method stores each endpoint descriptor into the driver's endpoint array to be used later for communication with the device. This completes the library task method of connecting to the USB device. Ideally, everything should be ready now for the exchange of data via the USB interface. My code, showing again, patiently waits for the connection and initialization to complete using this call to wait for connection, which uses the library's get USB task state each call to check if the state machine is at the running state. And if it is, then the be wait for connection variable is set false, and the execution then proceeds to perform the output of the AA cab bus command byte to the NCE USB interface board using the driver's send byte method here. The intention is to only execute the output once and follow that successful output with just one input attempt using the driver's receive bytes method here. I'm showing here the data output that is created by my 2 drivers, but it is essentially the same data for each. I'll show you. In this particular data, it was created using the bulk out endpoint 2 here and the bulk in endpoint 2 here. My driver's init method was called by the library when it detected the connection to the NCE USB interface board shown here. The library code then reads the NCE's configuration data and then calls my driver's endpoint extract method 3 times, here, here, and here, for each of the 3 endpoints defined in that configuration data. This message indicates the completion of the detection and configuration of the NC USB interface board. Here is where my driver calls its send byte method with the single AA for transmission to the USB interface. Now recall, AA was the request for the NCE PowerCab's firmware version. You can see that no error was detected in this USB out request, as it's indicated by this statement that send byte succeeded. Here is where my driver calls its receive byte method and in an attempt to perform the USB in request for the 3-byte response from the NCE PowerCab. The final result is shown here that the attached device did not respond. By the way, using the in endpoint for the interrupt endpoint produces a similar fail message, but it reads a little bit different. It says device did not respond in time. So I'm just not getting this thing to work, and I've invested an enormous amount of time to try to understand this entire process of the USB, the requirements, how the library works, and how to create an Arduino application that works with the library to communicate with the NCE USB interface board. So I've about had it. This is enough, and I think it's time to let the sun set on this entire process. And by the way, just in case anyone does ask, I did try to use it was this board right here. It's an RS485 Arduino interface board, and this would have allowed me to read the RS485 data coming directly from the NCE PowerCab, but I just couldn't get the timing to work. I'm using an Arduino Uno, and I don't know if it's just that it's not fast enough, but I could not get the data reliably from the RS485 interface. One kind of maybe humorous point about this guy was that I inadvertently connected the power from the NCE PowerCab to this one, forgetting that the NCE PowerCab supplies power on its RS485 to power up the remote controller, whatever that might be. And it's actually quite a lot more than this guy could take. So this is I bought 2 of them, and this is the one that survived. Once I hit that other one with that power, it just smoked immediately. The chip right here, it flared. It was interesting. It was like a bright flash, a little smoke trailing up. But that was my mistake, and that happens. Try and experiment with stuff. So let me conclude. My granddaughter created this drawing, and it really kind of struck me odd, because a young child who draws a train drew a steam locomotive. And you would think here in 2024 it would have been a little diesel locomotive, but she's got the smoke coming out of there and a little caboose coming along. I don't know about the windows. I didn't know passengers rode in the boiler, but that's pretty cool. That's pretty cool. Okay. Anyway, I've shared a lot of what is to me interesting information on a fairly wide variety of communication topics during my efforts to create a way to run the JMRI via the Bluetooth connection. I'm going to be 75 this coming November, and realizing that time flies by way too quickly, I do not want to invest any more time on the project at all. It's finished. My hope is that someone may encounter the information I've shared and somehow benefit by it and good luck to anyone else who tries any of this. It's pretty difficult, to me anyway. I mean, supposedly, there are much smarter people who probably could just ride right through all of this without any trouble, but not me. As I have the desire to access the abilities of the JMRI, my fallback plan solution will be to use this broken laptop. It's a fair performer, so I should think it will work just fine. I need to do something to prevent the display from breaking further. I don't know if it's possible to see that, but the display is actually cracked clear across here. And I think, to show you the reason for that crack is that this hinge, the design of the hinges on this laptop is such that you can fold the display completely back around and use the laptop in what I would call tablet mode. And I had this laptop for, gosh, I had it for about 4 years, maybe longer, maybe 5 years. And, you know, it works great, but I never ever folded the display back. I never once used it that way. And then one day, I know, 4 or like 5 years later, I decided, hey, you know what? This can be used as kind of like a tablet. So why don't I try that? So I folded it all the way back, and it was fine, but I didn't like it. Of course, I'm a keyboard man. So I took the display and started bringing it back up, and I heard crack, and apparently the hinge was too stiff. So by using the lever of the display, I managed to break out the whole corner. That entire corner is broken around the hinge, so that the hinge is actually not holding at all. It's all busted out. So I need to potentially address that small issue. And but the PC does work fine, even with the crack on the glass. It's just this glass over the front. So I'm going to take some time to think about how I might want to fix this, and maybe I could take and disconnect the display altogether, or maybe even use a monitor and remove this display entirely. But whatever I decide, it'll be something in the future. But in the meantime, I can use it as is. It'll work fine. I hope some of my advice and my diverse interest and my variable things that I call in Fun with HO stuff, the stuff part of it is appealing to some people, and I hope that whoever views these videos gets some benefit from having watched them. There's a lot of information in this series where I covered a lot of different kinds of communication methods. So thanks for watching. As always, I do appreciate anyone leaving comments. I do like comments. I like to read them. And if it should move you, you might leave a like. Do appreciate those as well. Thank you again, and on to the next one.